Bismillahirrahmanirrahim. Hello everybody. Today inshallah we are going to have our last tutorial, which is about the moments of inertia. Okay. Just as a quick review, MoI, the moment of inertia, like it measures the resistance of the body to rotation. Okay. In general, if we have an irregular shape, so let's say for example any shape, okay. So we can't use the direct equations. We should take a strip, a differential element. Okay, let's say it is dx. This is dx. Here is our differential element dA. Here is our function y in terms of fx. Okay, and here it is xy. So the equation will be what about the moment of inertia about the y-axis will be integral over a x squared over dA. Okay, in general it will be easier that if we are calculating the or want to get the moment of inertia about the y-axis. Okay, so we'll take the strip parallel to this axis that we are calculating the MoI about it. Okay, so uh, if we want to find Iy about the moment of inertia about the y-axis, we'll take a vertical strip. Okay, and also if we want to find like I about the x-axis, we'll take what differential element parallel to it, so it will be horizontal. Okay, and here it will be dy by x. Okay, dA equals to dy by x. Also another consideration, like why the function is it's easily expressed in terms of x. Say for example here y is equals to 1 over 8 x cubed. So our differential element dA is in terms of dx. Okay, and all the equation is in terms of x. So we have two considerations, but usually that if we want to calculate the MoI or IY, we'll take what differential element parallel to it. So it will be a vertical differential element. So here, let's say, but if we have like a rectangular shape, a circular shape, a triangular shape, we can find the MOIs, the moment of inertia using the equations, okay? Like here, if we want to find about the x-axis, the Ix, it will be what? Here, let's say it is h. It will be over x-axis, it will be 1 over 12 h cubed multiplied, let's say, by d or b, okay? So here the x-axis is intersecting this dimension, so this dimension will be cubed. Okay, and also we have, by the way, let's mention the parallel axis theorem. So if we have an area, okay, and the centroid is here, but it's required from us to find the moment of inertia about an axis, okay, parallel to this axis. So here it is I bar, okay, because it's passing through the centroid. But here, if we want to find the moment of inertia about this axis, we must use what the parallel axis theorem, which says, okay, I, which is about this axis, will equals to the centroidal moment of inertia, okay, which is I bar plus the area, okay, of this shape multiplied by the distance squared, which is what? Which is the distance from I bar till I, okay? So we can say it's in terms of x, Ix equals to Ix bar plus a dy squared, okay? And similarly, we can say Iy equals to Iy bar plus a dx squared, okay? And we have the polar moment of inertia J, which equals to Ix plus Iy. So let's begin here. Determine the moment of inertia for the shaded area about the y-axis. So it's about the y-axis, so it's better to take what? A differential element parallel to it, so it will be a vertical element, okay? Here, it will be dx, and the height of this differential element will be what? Not y, because here, at this point, at the curve, it will be x, x, y, okay? So this distance, so this vertical distance, small distance is y, so the rest, the remaining distance will be what? The total height, which is 8 minus this distance, which is y. So 8 minus y. Okay, so dA will be what? 8 minus y multiplied by dx. Okay, and here all points have same x tilde. So here it is x tilde, y tilde. We can note that here all the points in this differential element what have same x tilde. Okay. So now we can write our equation Iy equals to the integral x squared dA. Okay, so our integral will be from the limits of our integral will be from 0, okay, till 4, because we are integrating the differential element over this area. So x squared multiplied by dA, which is this one. Okay, we can do it by calculator or by hand, and we get the answer, of course, in uh, the units of length to the power 4 always. Okay. Now here we have regular shapes, so of course we will, like as we did in the previous chapter in centroids, we will divide our system into like small components, okay? And if we have a hole, we will like subtract it, okay? We'll put a minus, the area will be minus. So we'll determine the moment of inertia Ix of the shaded area about the x-axis. So here is our x-axis, okay, which is the reference, and it's required to find Ix. Okay. Here we must have the parallel, we must use the parallel axis theorem. Why? Because okay, we will say that the centroid, the moment of inertia of let's say the rectangle, this rectangle will be what in the middle here, of course, and also the moment of inertia of the circle will be also in the middle, but it's required here about this axis, so we will say okay, I bar plus the area of the rectangle multiplied by d squared, okay, which is the distance from this uh, axis to this axis, okay? And similarly here for the triangle, here will be the centroid, and so here it will be I bar, but at this, the amount of inertia about this axis will be I bar plus the area of the triangle multiplied by distance squared, okay, dy squared, which is this distance, okay? So here is our equation, okay? Now we can construct our table, but I prefer always in one equation to find Ix, because less time, less error, and less calculations. It's up to you. So our segments is are segment 1, segment 2, and segment 3. So here is segment 1, okay? The area of it will be what? 200 multiplied by 300, okay? dy will be what? The distance from this axis and this axis, because we are calculating Ix, okay, is what? The vertical distance, which is 150, okay? And Ix bar, we will say, okay, 1 over 12. Ix is part, the x-axis is intersecting which dimension? 300 millimeters, correct? So this dimension will be cubed. So 300 cubed multiplied by the other dimension, which is 200 millimeters, okay? So we can multiply now a dy squared, okay, and we can calculate Ix, which is Ix bar plus this value, okay. So this value plus this value will give us this value. Regarding segment number 2, here is segment number 2. So the area is what? Half multiplied by this length, 150 multiplied by the height, which is 300, okay. So half multiplied by 150 multiplied by 300 dy is the distance, as we said. Let's say here is the centroid, here is the y-axis, here is the x-axis. Now we are calculating ix, correct? Okay, and here is our reference for the amount of inertia about this axis. We want to calculate it. So the distance dy, the vertical distance, will be what? Dy. Yes, dy squared. Okay, so dy will be what? Remember the equation h over 3. Okay, the centroid. If we have a triangle, the distance from here to here and also from here to here is h over 3. Okay, so here we will say 300 over 3. Okay, which is this length 300 over 3. Okay, and regarding this, this distance will be 150 over 3. Anyway, here now ix bar will be what? 1 instead of 12 in the rectangle and the rectangular shape, it will be 36. So 1 over 36 multiplied by the x-axis is crossing which dimension? It's crossing what? The 300 dimension, correct? So it will be cube multiplied by the other dimension, which is 150. Okay, now we can get a dy squared, and adding these two numbers will get what? Ix over this axis, the x-axis. Okay, and finally, sorry about that. Let me fix that. Okay. Okay. Now regarding our third segment, which is the whole. Okay. The area of it is what? Pi r squared, but a negative value. Dy will have the distance from here till here. Okay. Because here is our x-axis regarding this segment, and there is the axis where we want to find the moment of inertia. So 150, the distance. Okay, ix bar is pi r to the power 4 over 4. This is the moment of inertia of a circle. Okay. Uh, what and the other part is the area multiplied by the distance squared. So it will be also negative. Okay. We will multiply them, the area by dy, and ix bar, we will add these two numbers. Okay, but don't forget the minus sign. Okay. And after taking the summation of all the segments, we'll get the final result. Or you can say, okay, in one equation, this is I bar plus a d squared, plus the second segment is what? I bar plus a multiplied by d squared, minus, here you will put a minus and open a big bracket. Okay. Otherwise, if you don't put a bracket, you should put here a minus and here a minus. Okay, otherwise you will get a wrong value in the calculator. If you just put a minus sign without a bracket, this will be a positive sign. Okay, so anyway, I bar plus a d squared, you will get the value. Okay, and in the calculator you can like divide. First of all, find this whole number. It will be this value. We'll get this value, and the second segment or the second term of the equation will get this number. Okay, because I think if you put all this equation in the calculator, you will not be able to do that. Okay, and you can note that we get the same result. So I think this will save very much time. Here this problem determine y uh, regarding chapter 9 the centroid which rotates the central axis, okay, from the for the t-beam, and then find the moment of inertia about the x prime axis. So here is the x prime axis. First of all, we need to find the centroid, which is the y bar. Okay, here x bar is what, 0, because it is at the axis, because it is symmetric about the y axis. So we need to find only y bar, which is summation of y tilde a divided by the summation of x, as we did in chapter 9. Okay, we'll divide this composite body into sections. Here is our first segment. Here is our second segment. So y tilde, here is our reference data. Okay, so regarding segment number 1, the centroid will, for it will be what, in the middle. We have a rectangular shape. So it will be 250 over 2, which is 125. Okay, so 125, the area is what, 250 multiplied by 50. Okay, plus the second segment, the y tilde will be what, the distance from, or yes, the distance from the center of this segment till the datum will be 250 plus 50 over 2, which is 25. So 250 plus 25 will be 275. And the area of it will be, okay, 300 multiplied by 50. Okay, and we can like copy the areas down. Okay, and we will get this, the y bar, to be 206.82 millimeters. Is it a reasonable number? Yes, because it is shifted like, towards the heaviest zone. Okay. Okay, here is the y tildes 125 and 275. Now we are ready to use our equation. It's required from us to find the moment of inertia about this axis. Okay, so we have to use the parallel axis theorem. Why? Because regarding segment 2, the center of it is here, and for segment number 1, it is here. Okay, so we will say summation. Okay, I bar for segment 1. Okay, we have a rectangular shape, so we will say, okay, 1 over 12, and it's about the x-axis, so this axis is intersecting this dimension, correct? So 250 or cubed multiplied by the other dimension, which is 50. Okay, plus a d squared. Now d squared or dy squared in this case is always, you can subtract this number, the y bar, by this number, okay, which is y tilde 1. Here it is 125, and the y bar is where, at the distance from the reference of 206.82. So you can say directly that this distance is what? Is just 206.82 minus 125, okay? Which is the distance from the centroid of the whole system, okay? And the centroid of this specific segment, okay? So 206.82 minus 125. Here again, regarding segment number 2, we have the x-axis is crossing what? 50 millimeters, so it's cubed, multiplied by 300, which is this dimension, okay? Plus a dy squared. The a, okay, it's easy, 50 multiplied by 300. Regarding dy squared, also, we can say directly 206.82 minus 275, okay, which is y tilde regarding the segment number 2. Or you can say here in the diagram, here is the centroid, correct? Here is the x-axis for this segment, okay? And the x-axis here for the centroid for the whole structure or system. So we want this distance, because we are using the parallel axis theorem, correct? So we can say, okay, here it is 206.82, and this distance is what? 275. So if we subtract them, we get this number, correct? And we'll get it in terms of millimeters to the power 4. Now here, uh, it's required to determine MoI about the x-axis and the y-axis. Okay. First of all, here the centroid is in the middle. Here it is in the middle regarding x bar and y bar because it is symmetric about the x-axis and the y-axis. Okay. So here we will use the parallel axis theorem. We will see. Let's start with the x-axis. Okay. Here is the x-axis. Okay. We'll divide our composite body into segments. So here we can note that this part, what the centroid of this part is the same as the centroid for the whole system. So here dy is 0. So if we are using the parallel axis theorem, it will be okay. I bar plus a dy squared, dy is 0. So it will this term will be cancelled out. So it is just like direct. It will be just 1 over 12. And here it's x-axis, so it's intersecting this dimension, which is 400. So 400, or sorry, not 400. We'll say, okay, 400 minus 20 minus 20. So 360. Okay, so 360 cube. Okay, multiplied by this small dimension, which is 20. Okay, which is 20. So here, regarding segment number 1, 1 over 12, 360 cube multiplied by 20. It's direct because the centroid again is on the centroid for the whole system. But regarding segments 2 and 3, okay, since it's symmetric, we can put here a 2, okay, multiply the bracket by 2. And here we must use the parallel axis theorem. Why? Because like the centroid for this segment, okay, is not the same as for this segment. So we have a vertical distance dy. So we must use the parallel axis theorem. We'll say, okay, here I bar will be what? 1 over 12, 20 cubed, because the x-axis is intersecting it, multiplied by what? 300, plus the area, which is 200 multiplied by 300, okay, and dy squared, which is this distance, okay? So here, what we have did, 1 over 12, 20 cubed multiplied by 300 plus the area multiplied by dy squared, which we can get it easily by saying, okay, this total distance is 360, okay, by saying 400 minus the total depth is 400 minus 2 multiplied by 20, okay, we'll give us 360. So if we say 360 over 2, we'll get this distance. And then if we say 20 over 2, we'll get the distance till the center. Okay, so it will be 190 squared. And we will get the answer. Okay, the answer will be this number, but here we can say that this part can be solved in another way by saying, okay, here I will take, just for your information, okay, I will take this whole rectangle and then subtract from it these two small rectangles. Okay, so here we will not use the parallel axis theorem. Why? Because here, okay, they will have the area will be minus negative, but the centroids are all at the same on the same axis. Okay, so Ix will be just 1 over 12, 400 cubed multiplied by 300, okay, minus 1 over 12, okay, considering this length, will be what? 280. 280, why? Because here, this total distance is 300 millimeters, and this distance is 20 millimeters. So 280 millimeters, okay, multiplied by the depth, which is, or the height, which is 360 millimeters. Here it is just 360 millimeters. We are subtracting these two small areas, okay? And again, we are not using the parallel act theorem because dy is 0, okay? Now here, the second part is determine the MoI about the y-axis. So here, regarding the first segment, what it is on the centroid. Here the centroid, okay, is here, x and y, okay, and for the whole shape, it's also here. Now regarding the other two segments, here is the centroid, correct, and here is the centroid. Now, what is the distance from the y-axis or the centroid from this small segment and the centroid for the whole segment? It is 0, correct? If it is, say, for example, here, we will say, okay, we'll use the parallax theorem and like the distance, this will be dx. Okay, so it will be iy plus a dx squared. But here, they are all on the same axis. So dy is 0. Okay, so we will say, okay, 1 over 12, 300 cubed. Why 300? Here, I'm starting with these two segments. So I multiply this by 2. And we are dealing now with the y-axis, iy. Okay, so it's crossing this dimension, so it's cubed, multiplied by the other dimension, plus this part, okay, which is 1 over 12, 20 cubed, which is this dimension, it's what? 20. And the y-axis is crossing this dimension, okay, the 20 millimeters, multiplied by the other dimension, which is 360. And we'll get the answer in millimeters power 4. Okay, so no need for the parallel axis theorem here. Dx is 0. Now, moving on to the final problem here. Determine the moment of inertia about the x-axis, okay, and determine the moment of inertia about the y-axis. Now, here the centroid location is given, but in the exam, like the first part can be, find first of all the centroid. Okay, so you use the summation x tilde a over summation of a, and y bar will be equal to summation of y tilde a over summation of s. So here it is given y bar is what? 30 millimeters plus 140 over 2, which is 100 millimeters, and x bar it's given 30 plus 70, which is also 100 millimeters. So starting with the x-axis, first of all, we should divide our system into what? Small segments, okay, regular shapes. So here what I did, I have divided this to segment number 1. Here it's segment number 2, okay, and here it is segment number 3. And we should, the second step, locate the centroids on them. So here we are starting with what? Ix, correct? So the centroids for segment number 1, we are now concerned with the vertical distance. Okay, so here it is the x-axis, and here the x prime. So we are concerned with this distance, the vertical distance dy. Okay, so first of all, here is our datum. Y1 or y tilde 1 will be what? Well, this dimension is 30, so it is just 15 millimeters. Okay, regarding y2, here it is 170, and here is the centroid, so it is 85 millimeters. Now, segment number 3, it will be what? 170, okay, 170 plus 30 over 2, which is 185 millimeters. So now we are ready to use a parallel axis theorem. Remember, for each segment, we should find this vertical distance. The distance from the centroid, or yes, the centroid for a specific segment till the centroid for the whole system, which is here. Now we are dealing again with x prime. So segment number one will be what? 1 over 12, 30 cubed. Why? Because the x-axis is crossing this dimension, which is 30. Okay, so 30 cubed multiplied by the other dimension, which is 170 millimeters. Okay, plus the area, which is 170 from here, 170 multiplied by 30, and dy is what? We will say, okay, here is our reference, correct? So if we say here it is 100, and here it is 15, so dy will be what? If we subtract these two numbers, we'll get this, which is the distance from the centroid of the whole system till the centroid of this segment number one. So 100 minus 15, okay? Plus the second segment, okay, which is, it will be 1 over 12. Here, the x-axis is crossing what? 30 millimeters, correct? So it's cube, and the other dimension, sorry, the x-axis is crossing over the 170 millimeters, so it's cube, multiplied by the other dimension, which is 30 millimeters. And the area will be what? Same, 30 by 70, 170, okay? Again, here, the distance, we should be careful. Here, we have found already that this distance, correct? Till the datum. From the datum till the centroid of segment number 2, which is 85. And we know that this distance is what? 100 millimeters. But dy is the distance from the centroid of this segment, segment number 2, okay, till the centroid of the whole system. Okay, so we need this distance. Okay, so we will say, okay, it will be just what? 85 minus 100. Okay, 85 minus this this like distance, which is 100 millimeters. So 100 minus 85 squared. Okay, now here, of course, the diagram is not to scale. Anyway, moving on to the third segment. Here is our third segment. Okay, here the x-axis is crossing which dimension? 30, so it will be cubed. 1 over 12, 30 cubed multiplied by the other dimension, and the area will be 100 multiplied by 30. And this distance will be what? Here we have found this distance from the center of segment number 3 till the datum to be 185. Okay, and we know here the distance is 100. So if we say 185 minus 100, okay, this distance will be dy, which is 85. Okay, so here it's 185 minus 100. So remember always dy or dx is the distance from the centroid of the segment till the axis where we want to find the moment of inertia about it. Okay, so we will use parallel active theorem. Here is d. In this case, it's dy. Okay, if we want to find like about x bar, okay, we'll find what the distance from the centroid, okay, till x prime, which is dx, and these will be squared in the equation, correct? And we will get the answer in millimeters to the power 4. Now, finally, about the y-axis. About the y-axis, here we have segment number 1, segment number 2, segment number 3. We should draw our axes. So here it's the y. Here it is the y axis for segment number 2. Here is the y axis for segment number 1. Correct? So we want to find this dx squared in the equation will be what? The distance from, let's say, the centroid of segment number 3 till the centroid of the whole system. So here it will be dx. Similarly, here it will be this distance dx. Okay. Okay, and also here it will be this distance dx. So it will be the horizontal distance from the centroid of a specific segment till the centroid of the whole system. Okay. Why the vertical distance? Because we are dealing now with y-axis, the y-axis. So we can draw easily the y-axis and the y-axis y prime for the whole system, and you can get the distances. Okay. So starting with segment number 1, here we have what? Y over 12, because it's a rectangular shape. Now the y-axis is crossing or intersecting which dimension? Here the y-axis is intersecting 170. So 170 cube multiplied by 30, which is the other dimension. Okay, and the area will be what? 30 multiplied by 170. And of course, that's why, as you can see, I don't recommend to use the table. Just put the equation and be careful. Okay, because the table, okay, it will take time and you will do more calculations, so the probability of error will be higher. Okay, and here you can divide this into two stages in the calculator. Okay, anyway, it's up to you. And here dx will be what? The distance here, x1, this distance here is the centroid for segment number 1, correct? So x, the centroid, is located, here is our reference, the y-axis, the datum. Okay, so here x1, it will have a distance of what? 30 millimeters. Here it is 30 millimeters. Okay, plus 170 over 2. Okay, so it is 115 millimeters. Okay, regarding, or let's one by one. So here dx1 will be what? 100. Here is this, the distance is 100, the centroid for the whole system. So we'll say 1 minus 2 squared. Okay, to get what? This distance, which is the distance from the centroid of this segment till the centroid of the whole system. So 100, here is 100, here is 100, minus 115, okay, to get this distance, okay, plus the second segment here. Where is our centroid? Here, okay, we are dealing now with the y-axis, correct? So from the datum, it will have a distance of what? Just 30, which is this distance, this dimension, divided by 2, which is 15 millimeters. Okay. And here we have 100 millimeters, the distance till the centroid of the whole system. So we'll say, okay, just 100 minus 15. Okay. To get this distance, which is the distance from the centroid of segment number 2 till the centroid of the whole system. Okay, so 15 minus 100. Here, in calculating dx or dy, you should be careful so much. So you will draw the axis, or you put the axis on each segment, and you will find the distance from the axis of this segment till the centroid, or yes, the centroid of the whole structure or system. So finally, segment number 3, we have what? We will say, okay, 1 over 12, we are dealing now with the y-axis, so it's crossing the 100 millimeters dimension, so it will be q multiplied by the other dimension, which is 30 millimeters, okay? And the area is, of course, 100 by 30, and dx will be what? Here is our axis. It's at a distance from the datum, is distance what? 100 over 2, correct? Because here it is 100, so just saying 100 over 2, here it is 50 millimeters. And the distance till the center of the whole system, which is y bar, is what? 100. So okay, if we say 100 minus 50, we will get what? This distance, which is dx. Okay, and again, the drawing is not to scale. So 50 minus 100 squared, and we'll get the answer in millimeters power 4. By this, we conclude our statics tutorial. So good luck in your exams, and thank you for your time.